Mac OS X as an Apple product is relatively new, less than a decade old, and replaces the older Mac OS that had been incrementally improved since 1984, when the first Mac was released. Cocoa and many other parts of the system are much older. The Cocoa APIs are an implementation of the OpenStep specification, which was the result of a collaboration between Sun and Next in the early 90s, and built itself on Next's earlier work. Next bought the rights to Objective-C in the 80s and, after some legal persuasion by the Free Software Foundation, contributed the initial implementation of the language to the GNU compiler collection. GCC and most of the other GNU build tools, such as GNU Make, are also available on OS X, and if you're bringing code from another platform where these are standard, such as Linux, then you may wish to use them on OS X as well. If you're starting from scratch, you'll probably want to use Xcode, which is Apple's IDE, and replaces the older projects builder that Apple inherited from Next. This contains all of the features that you'd expect from an IDE, including code editing, build system management, refactoring tools, and various other things. If you're coming to OS X development from some other Unix or Unix-like platform, then your first instinct is probably to start by firing up a terminal. You can do that on OS X. The terminal application is in the Utilities folder in Applications. You'll find all of the standard Unix tools available, as you'd expect, remembering that OS X is a fully certified Unix 03 platform. You can create Cocoa programs using Objective-C from any terminal-based Unix text editor. This is about the simplest Cocoa program that it's possible to write. The only Objective-C, as opposed to pure C, code in this example, is the Objective-C string literal, which starts with an @. The nslog function is a helpful Cocoa function, which logs the process ID, time, and a message. We can compile programs in exactly the same way that you would on any GNU platform, by invoking GCC directly. When we try this even with this simple file, however, there are some problems. Two symbols are missing. One is the class used for constant string objects, and the other is the nslog function. On almost any other platform, you'd fix this by providing a -l command line option, specifying the library to link. On OS X, GCC has a -framework option, and we use that instead. This provides the location of a bundle containing both a library and a set of headers. With this specified, the program compiles cleanly. Before we go on, let's take a look at the Cocoa framework. You can find it, and all of the other standard OS X frameworks, in the System, Library, Frameworks folder. A framework is a bundle, a directory with a fixed layout. It contains different versions of the library, headers, and any other resources that the library will require. Let's now have a look at the cocoa.h header file. This is the header file that you'll include in almost any Cocoa application, but it's actually very simple. It just includes 3 other headers. These, however, are very large. The pre-processed cocoa.h file is around 3 megabytes of text. Most of the time, you'll include this as the first header in every file in your project, so that you can use the pre-compiled version and avoid the need to pre-process and parse it for every single file that you compile. Although you can use the terminal for OS X development, it's quite unusual. It can be convenient for putting together very short and simple programs, but for anything larger you'll probably want to use Xcode. If you've installed the developer tools, either from your OS X install DVD or from the developer.apple.com website, then you should have a developer directory on your hard disk. This contains all of the developer tools, most especially a set of applications. We'll look at several of these, but the most important is Xcode, Apple's IDE. This handles project management, code editing, building, and debugging. It's closely tied to Interface Builder, which we'll look at in the next lesson. There are lots of templates for Xcode projects. The one you'll use most of the time is the Cocoa application, but there are specialized versions of this that include skeleton classes and resources for various frameworks, and even versions for different languages like Python and Ruby. The version of Xcode that I'm showing you now also has templates for Carbon, which is the framework based on the old MacOS Classic APIs. The version of Xcode I was showing you is the one that comes with Leopard. If you've upgraded to 10.6, then you'll probably see a window more like this one. A lot of the templates here have been consolidated. For example, there's now just one Cocoa application template with a couple of options, rather than different templates for core data applications, document-driven applications, and so on. If you want to create a command line tool, then, again, there's only one template, and you now select the frameworks that you want it to be based on as options. This applies a little bit less to creating frameworks and libraries, where there are still different templates for Cocoa and C frameworks, for example. One thing you'll notice is that Carbon has now gone. The Carbon APIs never made the switch to 64-bit, and Carbon is no longer supported as a development environment as of 10.6. Xcode isn't just used for application development. You'll also find templates for plugins for Apple applications, and even for the OS X kernel itself, with the kernel extension and driver templates. If you're porting code from another platform, then you may want to use the external build system template, and use that to drive your existing build infrastructure. We're going to start by creating a simple Cocoa project and have a look inside it. You can immediately see some of the files that are produced from this template. These are categorized on the left, with the folder icon indicating groups of files inside the project. These may correspond to on-disk folders, but typically don't. This project is linked against the Cocoa framework directly, and indirectly through that against the AppKit, Foundation, and Core Data frameworks. The project skeleton contains one class, which is set as the application objects delegate automatically. We'll look in a couple of minutes at exactly how that's done. This class contains a stub implementation of the application did finish launching delegate method, which is called when the application is launched. If we look at the main.m file, we see a typical Cocoa application stub main. This calls NSApplicationMain, which is a simple library provided function responsible for creating the NSApplication instance, loading the application's main nib file, and starting the run loop. This function does not return until the application exits. You can also see the prefix header file. As we saw in the comment in cocoa.h, this file contains pre-compiled versions of cocoa.h, making it much faster to compile source files that included this header. Code files aren't the only things in the project template. In the Resources folder, you'll see 3 files. The first of these is the property list that describes the project. If you look in any .app bundle, you'll find something very similar to this. This file is read when the application launches, and tells it, among other things, the name of the application class. The .strings file just contains localized versions of strings, and we'll look at the .xib file in more detail in the next lesson. This contains a serialized group of objects and defines connections between them, including the connection from the application object to its delegate. The target group tells Xcode what to produce and which files to use to produce it. Note that when we link against a framework, we can either make it weak or required.
Looking to advance your career by acquiring new skills? Tired of expensive off-site training programs? Wish you could learn from the best instructors in the industry? Look no further than LiveLessons, self-paced personal video instruction by the world's leading technology publishers. Each live lesson comes with a DVD featuring 3 to 4 hours of instructor-led classroom training, sample program code that allows you to work along with your personal instructor, and an example-rich study guide. Live lessons allow you to watch the entire course from start to finish, or navigate directly to any of the individual lessons. You'll literally watch over the shoulder of your instructor as he shows you how to build state-of-the-art applications. Live Lessons, the power of the world's leading technology experts at your fingertips. To learn more, visit mylivelessons.com today.